July 13th, 2025. In an ordinary observatory control room, the ATLAS survey team catches something no one expected: a new interstellar object, 3I/ATLAS, streaking past Earth. The discovery should have been impossible. Minutes later, astronomers realized their surveys missed it until the last moment. That's when the real panic sets in. If something from another star can slip through our defenses, how many more closer threats are still hiding in the dark? Alert: 3I/ATLAS was just the beginning. The Taurid swarm is next isn't just a warning about a cosmic visitor. It's the start of an urgent investigation into a shattered megacomet, hidden orbital traps, and a debris field waiting for its chance to strike. What are we truly missing, and how much time do we have left to find out? At 1:44 a.m. UTC, the Atlas control room is quiet, save for the hum of server racks and the soft ping of incoming data. 4 exposures, spaced over the last hour, have just been processed. The system's automated pipeline flags a faint streak: right ascension 16 hours, 16 minutes, declination just below 10 degrees north. The object moves at 2.13 arcseconds per minute, far faster than anything cataloged for this field. Its apparent magnitude is 20.8, barely above the survey's noise floor, yet the motion is unmistakable. A blinking alert flashes on the operator's screen. The protocol is clear: any uncatalogued, fast-moving object triggers an immediate review. Within seconds, an automated email pings the on-duty astronomer: unmatched fast-moving streak detected, review required. The operator leans in, scrolling through the stacked images. The streak holds steady across all 4 frames, its path cutting a shallow angle against the star field. No known asteroid, no comet, no satellite matches the trajectory. The system's internal threshold: apparent motion greater than 1.5 arcseconds per minute, streak length over 3 pixels, no catalog match within a 1 arc-minute radius, has been decisively crossed. 10 minutes later, the operator tags the candidate for urgent submission to the Minor Planet Center. The object's centroid positions are extracted, motion vectors measured, and parallax checked for confirmation. The initial submission lands on the Near-Earth Object Confirmation page by 2 a.m. UTC, flagged for global review. Atlas's principal investigator is copied on the alert, and within the hour, the team lead is on the line, verifying the object's apparent hyperbolic trajectory. The control room, now fully awake, buzzes with speculation. Is this another asteroid, or something stranger? By 4 a.m., the Minor Planet Center posts a preliminary designation: Provisional 3I/Atlas, the third interstellar object ever recorded, and it slipped past every survey until now. The realization settles in: if this is what the system catches, what else is moving unseen through the gaps? On Stargazer's Lounge, a user posts the first public mention of 3I/Atlas at 2:32 a.m. UTC. Within minutes, the thread fills with orbital calculations, code snippets, and raw astrometry. Someone runs the numbers through find_orb, an open-source trajectory tool, and posts a preliminary orbit: hyperbolic, inbound, and uncatalogued. By 3 a.m., amateur astronomers across 3 continents are feeding fresh measurements into the model, refining the path with each new data point. Reddit's r/astronomy lights up with speculation. Is this truly interstellar? How did every major survey miss it until now? A pattern emerges as users compare sky coverage maps from Atlas, Pan-STARRS, and ZTF. Gaps appear: patches of sky left unmonitored for hours, sometimes days, due to weather, moonlight, or simple scheduling limits. One contributor overlays the object's sky path on a global survey map. The result is sobering. For nearly 12 hours, 3I/Atlas traveled through a blind corridor, invisible to every professional instrument. Only a chance overlap with the Atlas schedule revealed it at all. Forum analysts dig deeper, sharing scripts that simulate hundreds of random inbound objects. The results show that with current coverage, faint, fast-moving bodies, especially those with unusual orbits, can slip by undetected unless everything goes right. Several users reference near misses like 2019, OK, and 2021 UA1, both discovered only after passing dangerously close to Earth. The conversation shifts from excitement to concern. If a single detection depends on a lucky alignment of weather, timing, and human vigilance, what else is out there, moving unseen? The collaborative effort produces a full orbital solution in just under 4 hours, faster than most institutional teams. Yet the process exposes a deeper problem. Even with a global network of professionals and amateurs, Earth's watchfulness is patchwork at best. The crowd's verdict is clear. The system works, but only just. For every 3I/Atlas that gets spotted, how many more are lost in the gaps? 20,000 years ago, a single comet swept through the inner solar system, a frozen nucleus, 40 kilometers wide, trailing a luminous tail across the night sky. Unlike the fleeting visitors that pass harmlessly, this giant was doomed to fragment. Under the relentless pull of the sun and the tidal tug of Jupiter, its structure began to fail. Ice vaporized, pockets of gas exploded outward, and cracks spidered through the body. The process was violent but slow, stretching over centuries. One by one, colossal shards broke free, each carrying the memory of the parent's original orbit. Planetary scientists now reconstruct this event through thermodynamic breakup models and orbital simulations. They trace the debris field that remains, a vast, invisible river of rock and ice, stretching millions of kilometers wide. The largest fragments, some the size of city blocks, still lurk in the stream, drifting alongside countless smaller stones and dust. Over time, gravitational nudges from Jupiter herded many of these pieces into a precise resonance, synchronizing their paths and locking them into a slow dance with the giant planet. Today, the only visible remnant of that ancient catastrophe is Comet Encke, a battered, short-period comet that completes an orbit every 3.3 years. Encke's orbit is a living fossil, matching models of the original megacomet's trajectory. But Encke is just the tip of the iceberg. The true scale of the Taurid stream is almost unimaginable. Hundreds of millions of objects, from grains of sand to kilometer-wide boulders, all sharing a common ancestry. For Earth, this means that twice each year, our planet plunges through the debris cloud, exposed not just to harmless meteors, but to the possibility of encounters with much larger, darker fragments. The breakup that created the Taurid swarm was not a single explosion, but a rolling sequence of disintegrations, each one scattering more debris into the inner solar system. Thermodynamic models show that as the original nucleus spun apart, it seeded a debris field so broad that it now forms the largest coherent threat to Earth in our cosmic neighborhood. Every fireball, every slow-moving meteor that lights up the autumn sky is a distant echo of that ancient disintegration. The Taurid swarm is not a myth or a minor shower. It is the legacy of a planetary-scale disaster, still unfolding in slow motion above our heads. Jupiter's gravity acts like a cosmic metronome, setting the rhythm for the Taurid swarm. Every 7 orbits of Jupiter, the densest clusters of Taurid debris align with Earth's path, an arrangement known as the 7-to-2 orbital resonance. This cycle repeats roughly every 3,300 years, concentrating fragments into a corridor that sweeps across our planet's orbit. The mathematics behind this resonance isn't just theoretical. It's confirmed by real-world data, bolides recorded by NASA's All-Sky Fireball Network, and velocity statistics from meteor camera arrays around the globe. During late October and early November of 2015, the All-Sky Fireball Network registered a sharp spike in slow, bright fireballs. These events didn't come from random directions. Their trajectories traced back to the Taurid radiant, and their entry speeds clustered tightly between 27 and 29 kilometers per second. Analysts noticed that these fireballs appeared in clusters, sometimes 3 or 4 in a single night, matching predictions from N-body simulations of the swarm. The same pattern reappeared in 2019, with another surge of Taurid fireballs lighting up the sky. Each event was logged, triangulated, and cross-checked by both professionals and citizen observers who submitted hundreds of independent reports to meteor societies and online forums. The resonance acts as a gravitational trap. Fragments that drift into the 7-to-2 ratio with Jupiter become locked into a slow drift, their orbits stretched and compressed until they form dense streams. These trapped bodies can linger for thousands of years, gradually spreading out but still returning in swarms when the timing aligns. Orbital simulations show that during peak swarm years, Earth's risk of encountering a meteor-scale Taurid fragment rises by a factor of 10 or more. The evidence isn't just on paper. All sky cameras have captured not only the meteor showers, but also rare, massive bolides, some bright enough to cast shadows, others slow enough to be mistaken for re-entering satellites, yet always with the telltale Taurid signature. This cycle of danger is not hidden in ancient myth or buried in scientific journals. It's visible in the raw data: bolide clusters, radiant maps, and fireball velocities. The 7-2 resonance explains why the Taurid threat is not a constant drizzle, but a periodic storm. And every time the cycle completes, the odds of a Tunguska scale encounter rise again, waiting for the next alignment. At 7:17 a.m. on June 30th, 1908, a shockwave swept across the stony Tunguska River in central Siberia. The blast flattened 80 million trees in a radial pattern, scorching the trunks and snapping branches as if they were matchsticks. Eyewitnesses in nearby villages described a column of blue-white light, followed by a searing heat and a thunderclap that shattered windows 200 kilometers away. Herds of reindeer were hurled to the ground. For days, the night sky over Europe glowed with strange silvery clouds, bright enough that people could read newspapers at midnight. No crater marked the ground, only a tangled wasteland stretching more than 2,000 square kilometers. Seismic stations as far as England recorded the tremors. Later analysis put the explosion's power between 5 and 15 megatons of TNT, 1,000 times the force of Hiroshima. The epicenter, mapped decades later by Soviet scientist Leonid Kulik, revealed a butterfly-shaped pattern of devastation. Trees at ground zero stood upright but stripped bare, while those farther out lay flat, radiating away from a single point. Kulik's expedition in 1927 found no fragments, no impact pit, just scorched earth and a wilderness still recovering from the blast. The absence of a crater pointed to an airburst. A cosmic intruder, likely a fragile comet or dark asteroid, had disintegrated at an altitude of 5 to 10 kilometers. The Tunguska event remains the largest modern impact, a warning written across the Siberian forest in living wood and silent stumps. The scale of destruction reveals what even a modest fragment from the Taurid swarm could unleash if fate aligns the orbits once more. 12,900 years ago, a thin layer settled into lake beds and peat bogs across 4 continents. Chemists sifting through these sediments find a cocktail of platinum spikes, magnetic spherules, and nanodiamonds, materials only formed under crushing heat and pressure. The same layer, called the Younger Dryas boundary, coincides with a sudden return to Ice Age cold, the extinction of mammoths and saber-tooths, and the collapse of the Clovis culture. Geochemists like James Kennett and Adrian Malott examine melt glass and high-temperature carbon, pointing to an airburst or a cluster of airbursts, not volcanic eruptions or wildfires. The distribution is too broad, the markers too exotic. Further north, in Greenland's ice, another signature appears: a sharp rise in platinum and iridium, elements rare on Earth's surface but common in cosmic debris. These traces echo the fallout from a cosmic event, possibly a swarm of comet fragments detonating in the atmosphere. The evidence stretches from North America to Turkey, where ancient carvings at Göbekli Tepe, may record a sky full of falling fire. Fast forward to 1962. As the Soviet Mars 1 probe crosses the Taurid stream, its micrometeoroid counter ticks up, registering impacts every 2 minutes. Controllers in Moscow watch as the instrument logs a barrage of tiny strikes, each one a microcosmic echo of the ancient debris field. The data confirm what orbital models predict. The Taurid stream is not just a meteor shower, but a vast, persistent hazard that extends far beyond Earth's atmosphere. In the late 1970s, Victor Klube and Bill Napier gather these threads. They argue that cosmic impacts are not random accidents, but follow cycles driven by the slow resonance of debris trapped by Jupiter. Their theory, coherent catastrophism, faces skepticism, but the evidence, ancient sediment chemistry, modern probe data, and orbital simulations, keeps accumulating. The pattern is clear. Earth moves through epochs of heightened risk, written both in the rocks below our feet and in the empty silence of space. Beyond the familiar meteor streams, a different class of threat circles the outer solar system. Giant icy bodies, known as centaurs. These objects drift between Jupiter and Neptune, their orbits unstable, their futures unpredictable. Recent population models suggest there are over 1 million centaurs larger than a kilometer, most still undiscovered and untracked. Each one represents a potential parent to new swarms of debris, capable of evolving into short-period comets or breaking up into clouds of hazardous fragments. Orbital dynamicists run simulations that show how the gravitational pull of Jupiter and Saturn can nudge these bodies onto planet-crossing paths, sometimes with little warning. Yet size isn't the only problem. Infrared sky surveys, like NASA's NEOWISE mission, reveal that about 60% of near-Earth objects are dark, so-called low-albedo bodies that reflect almost no sunlight. These dark comets and asteroids can slip through optical surveys, remaining nearly invisible until they are dangerously close. Some show only a faint trace of outgassing, just enough to betray their presence. For planetary defense teams, this means that even the most advanced telescopes are missing a large fraction of potential impactors. The true census of hazardous objects is still incomplete, and the next threat may already be inbound, hidden in the darkness beyond Jupiter. In September 2022, a spacecraft called DART slammed into the asteroid Dimorphos at over 6 kilometers per second. The impact nudged the asteroid's orbit, proving for the first time that humans can alter the course of a small body in space. Planetary defense leaders hailed the test as a turning point, evidence that, with enough warning, a threat could be deflected. Yet, the celebration comes with a caveat. DART targeted a slow, well-tracked asteroid. The real challenge lies with comets and centaur fragments, bodies that approach at tens of kilometers per second, often discovered only months before a possible impact. For these, kinetic impactors may be too slow, and the warning too short. NASA's next hope is the NEO Surveyor mission, a space-based infrared telescope designed to spot dark, faint objects years before they cross Earth's path. But budget delays have pushed its launch back, leaving a gap in global vigilance. Policy briefings stress this vulnerability. Most dark comets remain invisible to current surveys, their arrival masked until the last moment. Some astronomers turn the question outward. If advanced civilizations exist elsewhere, how would they track the cycles of debris and fire that sweep through their skies? Would they see the periodic scars on planets and wonder about the forces shaping their own histories? For now, Earth's best defense is vigilance, an uneasy balance between growing capability and the vast, unpredictable cosmos. In 1908, a single Taurid fragment leveled 80 million trees in Siberia, an event now traced to the same debris field Earth still crosses every year. The Taurid stream, born from a megacomet breakup 10,000 to 20,000 years ago, has left impact markers from the Younger Dryas to modern times, as confirmed by sediment analyses and fireball records. Yet, over 1 million centaurs larger than 1 kilometer remain beyond Jupiter, and up to 60% of near-Earth objects may be dark, nearly invisible to current surveys. While NASA's DART mission proved we can deflect small asteroids, kinetic methods remain untested against fast, volatile comet fragments. Key data on object composition and orbits remain incomplete or classified, and the exact timing of future dense swarm encounters is still debated. The evidence is clear. Cosmic threats are not distant possibilities, but recurring realities. Our planet's history and future are shaped by cycles we are only beginning to understand.